Welcome to AI Paper Podcasts, the show where we dive deep into the research you care about.
Today, we're tackling a paper you shared with us, looking at this really interesting challenge. Getting large reasoning models to handle, well, seriously long texts using reinforcement learning.
Yeah, the paper's titled Quenlong L1, Towards Long Context Large Reasoning Models with Reinforcement Learning.
Okay, so before we really get into the weeds, let's do that quick rundown, like the 1-minute version for you.
Good idea. So here's the basic challenge. RL, reinforcement learning. It's been great for making LRMs better at reasoning, but mostly on shorter stuff.
Right. But when you try to scale that success up to, say, documents with over 100,000 tokens, you hit some major roadblocks.
Yeah, training becomes super inefficient, and the whole optimization process can get pretty unstable.
So this Quenlong L1 paper, it introduces a new RL framework to tackle exactly that, using something they call progressive context scaling.
And it's got three main parts to it. First, there's a warm-up supervised fine-tuning, or SFT phase, basically gets the model ready.
Then number 2 is curriculum-guided phased RL. This helps keep things stable as you gradually increase the context length the model sees.
And third, they use difficulty-aware retrospective sampling. This makes sure the model keeps trying to solve the really tricky problems it encountered before.
And the punchline. Their model, Quenlong L1 32B, actually achieves state-of-the-art results on a bunch of these long context document QA benchmarks.
Yeah, it performs right up there with models like Claude 3.7 Sonnet Thinking and beats others like OpenAI o3 Mini. Pretty impressive.
So for this deep dive, our mission is to really unpack what makes this long context reasoning with RL so difficult.
And then explore how this Quenlong L1 framework actually works, how it addresses those problems head on.
Right, looking at the specific techniques they used and the results they got in the paper you sent us, it offers a kind of new recipe for building these more capable LRMs.
Okay, so let's start with the context. As you know, RL has been, well, pretty transformative for LRMs.
Definitely. It's helped push them beyond just predicting the next word, improving how they reason step by step, especially on shorter tasks.
We've seen things like chain of thought, these slow thinking strategies, really get a boost from RL, sometimes hitting human expert levels in specific narrow domains.
But that success, like you said, is often in context of maybe, 4,000, 8,000 tokens-ish?
Exactly. And where it gets really tricky and frankly quite interesting is trying to scale those same RL techniques up to genuinely long contexts. We're talking 120,000 tokens. Like in this paper.
Yeah, that's a whole different ballgame. It's a critical challenge, and it's not just a matter of feeding the model more text. The paper actually digs into why it's so hard. Figure 2 gives some good clues.
Right. First big issue, suboptimal training efficiency. What happens is when you train on these huge contexts, the model's output entropy.
Which is kind of like its willingness to explore different answers or reasoning paths.
Exactly. That entropy drops really fast early in the training, so the model becomes less exploratory.
Which means it's slower to find better strategies, slower to improve its reward. It gets kind of stuck.
Like it keeps trying slight variations on a theme instead of finding a fundamentally better approach to navigate all that text.
Makes sense. And the second problem they highlight.
Unstable optimization. Longer outputs, plus the fact that these long documents vary a lot in length naturally, introduces way more variance into the training gradients.
Ah, okay. So that leads to bigger fluctuations in things like the KL divergence, that measure of how much the policy changes each step.
Precisely. You get these really big swings, making the whole RL optimization process jittery and, well, difficult to get it to converge reliably.
So what does this mean for you, the listener, practically?
Well, this difficulty in applying RL effectively to long contexts is a major bottleneck.
Yeah, if you want an LRM to act like, say, a legal analyst digging through contracts or a researcher summarizing long papers, you need it to ground its answers firmly in that text. Without solving this RL scaling issue, models often just fall back on their general knowledge, which isn't what you want for tasks needing high fidelity to the source document.
And which brings us neatly to their proposed solution, the Quenlong L1 Framework.
Right, designed specifically to bridge this gap, take the skills learned on short tasks and make them work robustly in long contexts using RL in a stable way.
And the core idea, which they mention is inspired by some recent pre-training work, is this progressive context scaling during the RL phase.
Don't just jump into the deep end with 120K tokens on day one.
Exactly. Ease into it. And figure 3 in the paper lays out the framework. It has 3 key components working together. First up, warm-up supervised fine-tuning, or SFT.
And the logic there is You need a solid starting point before you throw the RL complexity at it.
Precisely. You need a robust initial policy. Get those fundamentals down. First, basic context understanding, pulling out information, generating sort of plausible reasoning steps.
So how did they build that initial policy?
They trained it on about 5,300 high-quality examples, question, document, answer triplets. These are actually distilled from a more powerful teacher model.
Okay, using standard SFT. And crucially, this warm-up SFT was done using a limited context length, what they call L1. So shorter context to start. Right. Master the basics on shorter, clean data first. Then comes the RL, but not all at once.
No, that's the second component. Curriculum-guided phased reinforcement learning. The goal here is stability and gradual adaptation.
So instead of one giant leap to long context,
they break the RL process into discrete phases, let's say K phases. Each phase, LK, targets a progressively longer range of input lengths.
So in phase K, you'd train on examples where the total length is somewhere between the max length of the previous phase, K1, and the new max length for phase K.
Exactly. And in their experiments, they used a two-phase curriculum. Phase 1 went up to 20,000 tokens, L1, and phase 2 went up to 60,000 tokens, L2.
That makes intuitive sense. You gradually increase the difficulty. Okay, what's the third piece?
Difficulty-aware retrospective sampling. This one's all about making sure the model doesn't just learn the easy stuff. It needs to keep exploring and get better at the examples it finds genuinely hard.
Okay, how do they define hard in this context?
They calculate a difficulty score for each training instance. It's based on how well the base model did on it initially, specifically. It's the inverse of the average reward the base model got for that question.
So if the base model really struggled and got low rewards on average for a particular question, that question gets flagged as high difficulty.
Right. And then they use that score for importance sampling, meaning those harder instances, especially ones from previous training phases, are deliberately oversampled in the current phase's training data.
So you keep reminding the model of the problems it struggled with, forcing it to get better at them.
Exactly. Keeps pushing the boundaries. Now, actually doing the RL optimization, they ran into another challenge with standard algorithms like PPO.
Oh yeah, the ones that usually rely on a value network.
Right. Why was that a problem here?
Well, it comes down to compute. The attention mechanism in transformers has that quadratic complexity compute cost scales with the square of the sequence length. Training a separate value network that also has to look at the entire super long context at every step, it just becomes computationally prohibitive. It blows up.
Okay. So the main model generating the text can handle the long sequence, but training a second network, the value predictor, to also process that same long sequence is just too much.
That's the issue. So they switched gears. They used what are called group relative RL algorithms, specifically GRPO and DAPO.
And how do those work around the value network problem?
They estimate the advantage, basically how much better one generated output is compared to others for the same input by normalizing the rewards across a group of outputs generated for that one input. Clever, right?
Yeah, it avoids needing that expensive separate value network entirely.
GRPO is a bit simpler. It actually drops the KL terms sometimes for more exploration. DAPO adds a few extra techniques for stability, like dynamic sampling.
Okay, and they also needed a specific reward setup for this long context QA task, didn't they? Just checking for an exact match isn't really sufficient.
Definitely not. Especially with complex reasoning over long texts, answers can be phrased in many valid ways. A super strict rule-based reward might punish perfectly good answers.
Right, it could limit exploration and actually hurt performance if the model gets scared to try slightly different phrasing.
So their solution was a hybrid reward mechanism. It tries to balance precision with semantic correctness.
How does that hybrid approach work?
Two parts. First, rule-based verification. This gives you precision. It does strict checks like, is the extracted final answer string exactly the same as the gold answer string?
Okay.
But, and this is important, they deliberately left out rewards for just formatting things correctly in the intermediate steps.
Why is that?
Because the base model was already pretty decent at formatting. They found that rewarding format too much during RL actually made the model focus on the easy part, the format, and distracted it from learning the harder part, the complex reasoning chain.
Interesting. So just check the final extracted answer for the rule-based part. What's the other part?
LLM as a judge. This complements the strict rules. It uses a smaller language model. They use Quinn 2.5 1.5b at temperature 0 for consistency to check if the generated answer means the same thing as the gold answer, even if it's worded differently.
So it catches those cases where the answer is semantically right, but may be extracted or phrased slightly differently. Handles false negatives from the strict check.
Exactly. And the final reward the model gets for an output.
It's just the maximum of the two scores. If either the strict rule check or the LLM judge says the answer is good, the model gets a positive reward for that generation.
Nice. Balances precision and recall, essentially.
Okay, that covers the framework and the reward. Let's talk experiments. The task they focused on, as you mentioned, was document question answering, .QA.
Which makes perfect sense. It inherently requires both understanding the long document and doing potentially multi-step reasoning.
They used a few data sets. For the main RL training, DOCQA RL 1.6K, about 1,600 problems needing different kinds of reasoning, like mathematical, logical, multi-hop.
And Table 3 shows these are genuinely long contexts. Average length around 11,000 tokens, max up to 60,000 in the training set itself. And some evaluation benchmarks pushed even further, up to 176K tokens.
Wow, yeah. And for the initial SFT warm-up, they used a separate 5.3K dataset of high-quality distilled examples, making sure those were within the shorter L1 context limit, like 20K.
They started with R1 distilled QM-based models, both 14B and 32B parameters, applied their two-phase RL curriculum 20K, then 60K max lengths, and that difficulty-aware sampling.
And they mentioned the scale needed 32 A100 GPUs, so not a trivial training setup.
No, definitely not. For evaluation, they tested on 7 standard long context .Q benchmarks. They pushed their Quenlong L1 models up to 120K tokens at inference time.
Which is often longer than the baselines could handle, right? Some were limited to 50K?
Yeah, depending on the baseline model's architecture. And the metric they used for evaluation was accuracy specifically, the max of either an exact match or being judged correct by another LLM judge, DeepSeek V3 in this case, again at temperature 0. It mirrors their training reward.
And the baselines they compared against were pretty comprehensive. A mix of proprietary and open source models, Claude 3.7, Sonnet Thinking, OpenAI O3 Mini, Gemini models, DeepSeek R1, others.
A real who's who. So the findings, Table 4 and Figure 1, really tell the story.
First off, just doing SFT, even long context SFT, didn't move the needle much on these complex reasoning tasks. The gains were small, maybe a point or two on average, and really inconsistent across benchmarks.
So SFT helps get things started, but it's not the key to unlocking top performance here.
Not at all, but the RL integration, that was the game changer.
Yeah, a big jump in performance. The Quenlong L1 models showed average gains of like 4 to 5 points over the base SFT model, way more than just more SFT gave them.
This really underscores that key takeaway. RL seems indispensable for refining the model's ability to handle these complex, long context reasoning problems effectively.
And the headline result. How do they stack up against the competition on these specific tasks?
Well, the Quenlong L1 32B model achieved an average accuracy of 70.7%. That matched Claude 3.7 Sonnet Thinking, which also scored 70.7% in their eval.
Wow, okay, so right at the top.
Yeah, and it surpassed several other strong models like OpenAI O3 Mini at 70.4, Qwen 3 Plus at 70.3. Even their smaller 14B Quenlong model did really well, beating larger models like Gemini 2.0 Flash Thinking and the base Qwen 3 32B.
So based on the results, this Quenlong L1 framework puts these models right at the state-of-the-art for these kinds of long context .QA benchmarks.
They also looked at test time performance scaling using pass at K. Right, generating multiple answers.
Yes, Figure 4 shows that. If you let the model generate, say, K different potential answers and check if any of them are right, the performance goes up.
And their Quenlong L1 14B model, even with just pass at two attempts, hit 73.7% average accuracy.
Which actually beat DeepSeek R1 and OpenAI O1 Preview in their pass at K comparison. Suggests the model has good exploration capabilities. It can generate diverse, potentially correct reasoning paths.
And the gap between pass at 1 and the higher pass at K scores suggests there might still be room to improve how the model focuses its search during training.
Definitely. They also did ablation studies, which are always important. Got to check if each piece of their proposed framework actually matters.
Absolutely. And Figure 5 shows the results. What did they find?
Well, first, removing the warm-up SFT hurt performance. Figure 5b suggests it's really needed for a stable and efficient start to RL. You get faster reward gains and lower gradient norms early on.
Okay, so the warm-up helps. What about the phased RL curriculum versus just trying to train on long contexts in one go?
That was crucial too. Figure 5c shows that single-stage RL on the long context was much less stable. You see bigger KL fluctuations, even potential entropy collapse where the model stops exploring.
So the curriculum with its phases really helps stabilize that adaptation process.
Yeah, significantly better performance compared to the single-stage approach. And the third component, the difficulty-aware sampling.
That added further gains. Figure 5D is interesting. It shows that even after the first phase of RL, those examples flagged as difficult still tend to have low reward and high entropy for the model.
Meaning the model still hasn't fully mastered them.
Exactly. So strategically resampling them in the next phase keeps pushing the model to improve on the hard stuff. It works.
Beyond just validating their framework components, they also dug into some deeper analysis. Figure 6, looking at the SFT versus RL trade-off, seems particularly insightful for anyone building these models.
Oh, this is really interesting. They did a comparison. Apply RL after doing short context SFT up to 20K tokens versus applying RL after doing long context SFT all the way up to 120K tokens.
Okay, and the long context SFT model, just by itself, was better than the short context SFT model, right?
Right.
Which makes sense. More SFT data usually help.
Right, and long context SFT, while compute intensive, is still generally cheaper than doing massive RL training.
But here's the kicker.
Here's the kicker. When they applied RL on top of the already pretty good long context SFT model, the extra gain was tiny, like 0.3 points.
Huh, okay.
But when they applied RL to the short context SFT model, the gain was much larger, 3.2 points.
Wow, okay, so what does that suggest?
It strongly suggests SFT and RL play different complementary roles. SFT is great for getting a solid baseline relatively efficiently.
But if you want peak performance, RL is essential. And maybe doing too much SFT first actually hinders how much RL can improve things later.
That seems to be the implication. It might push the model into a local optimum that's hard for RL to escape. So for you practitioners, the takeaway might be, don't overinvest in SFT if your goal is maximum performance. Prioritize getting to RL sooner.
That's a really valuable insight. You can't just SFT your way to the top on these complex reasoning tasks.
Seems not. They also did this fascinating analysis, shown in Figure 7, tracking specific reasoning behaviors during training. Things like grounding.
Like checking back with the document.
Yeah. And sub-goal setting, backtracking, verification, these kinds of internal reasoning steps.
And what patterns do they see in how these behaviors change?
Well, all models showed these behaviors somewhat. Grounding was most frequent, which makes sense for DocQA, but the key finding was that RL training progressively amplified these behaviors.
Amplified them, meaning the model did them more often.
Exactly. As RL training progressed through the phases, the model used grounding, backtracking, verification, etc. more frequently. And critically, this increase in reasoning behavior correlated directly with the performance improvements.
Whoa, so it's like RL isn't just teaching the model the right answer, it's actively improving how the model thinks, how it processes the information to arrive at the answer.
That's certainly what the data points towards. RL seems to be shaping and strengthening the underlying problem-solving process.
What about SFT? Did it also increase those behaviors?
Interestingly, yes. SFT also led to more of these behaviors compared to the base model. But this is the key difference, that increase from SFT didn't translate into the same kind of performance gains that the increase from RL did.
Highlighting that difference again, SFT is more like imitation, pattern matching, while RL is about developing and optimizing a functional skill.
Precisely. And the case studies they included really make this concrete. Take case Quenlong Testimony 183, extracting some financial info from a long text.
What happened there?
The base model just made calculation errors, got distracted. The SFT model, even after fine-tuning, got completely lost. It started looping through irrelevant parts of the document and actually hit its token limit before finding the answer.
Ouch. But the Quenlong L1 model?
It navigated it much better. The case study shows it might explore a wrong path initially, but then it uses those behaviors or RL amplified, like verification and backtracking. It explicitly says things like revisiting the document, filtering irrelevant info, questioning previous steps.
Ah, so it uses self-correction.
Yeah, it grounds itself back in the relevant text and eventually finds the correct answer. It's a clear example of how those enhanced reasoning behaviors helped it succeed where the others failed due to the complexity and length.
Okay, so wrapping up this deep dive then. The Quenlong L1 paper makes a strong argument for their progressive scaling framework being a successful way to apply RL to long context reasoning.
Yeah, they achieved leading performance on these tough DocQA tasks and, maybe more importantly, gave us some key insights for building better LRMs.
Like the need for progressive context scaling for stability, the distinct roles of SFT and RL, with RL being key for top performance, and how RL seems to foster these beneficial reasoning behaviors.
And they also point towards future work, right? Pushing these ideas further.
Definitely. Things like tackling even harder real-world tasks, maybe scientific research, complex video analysis, also developing more advanced architectures, perhaps better attention mechanisms for length.
And even rethinking the RL paradigm itself for potentially infinite contexts. Maybe moving beyond token-level rewards to thinking about turn-level interactions or something else entirely.
Lots to explore. Which brings us to our final thought for you, the listener, to mull over after diving into this paper with us.
Consider that finding. RL training specifically amplifies reasoning behaviors like grounding, backtracking, verification. What does that really imply about what these models are learning?
Is it just about optimizing for the right output? Or, as the evidence seems to suggest, is RL actively shaping the internal process, the how, of thinking through complex problems in these data-rich environments?
And if that's true, what does it mean for our potential to build LRMs that are genuinely more adaptable, maybe even more intelligent, in the future?
It certainly suggests a fascinating path forward, looking not just at the what of model answers, but the how of their reasoning strategies.
Thank you for joining us for this AI paper podcast, digging into Quenlong L1 and the challenges of long context RL based on the sources you shared. We hope this gave you some valuable takeaways.
Keep exploring, keep questioning. Join us next time on AI Paper Podcasts.